Welcome to this video on a continuation of function composition. We're going to be looking at some word problems to start off with. In this first one, we have an oil tanker that's leaking oil in a circular oil patch, and we have the radius of that oil patch is increasing at a rate of 3 feet per minute. So we can see our first function here, r of t, is that our radius, 3 times the number of minutes, will be how much the radius has increased by. And then we have another formula beneath it where you have the area of a circle is determined by pi times the radius squared. And so a way we could write both of these, remember that we could write this as r equals 3t, and then we could also have this as a equals pi r squared, like that. So now what we have to do here is we basically have to evaluate, well, after 2 minutes, how big of a radius of a circle is going to be, and then use that answer for the radius of our new problem. So what basically we're doing here in this first problem is that we're writing it out as the area being the outer function and the radius in terms of t being the inner function. So we have something like this. So now if I wanted to kind of set that up in my problem here, I have my pi times 3t squared. I entered 3t in where the r was before. And if I kind of figure out what that equal to, it'd be pi times 3t times 3t, which would end up being equal to pi times 9t squared. And then we just have to evaluate this new function right here after 2 minutes and after 5 minutes. So for 2 minutes, we would do pi times 9 times 2 squared. And we can find our answer for that. So second, pi, and then we got times 9 times 2 squared. So 113.1. 113.1 feet after 2 minutes. And then we can set up pi times 9 times 5 squared would then be equal to 706.9 feet. So 3 minutes later, it is a much larger circle. As you can see that we have two different functions that are having multiple different variables increase at once, and that is where you kind of see the more high-level math coming in with function composition. Moving to our second word problem example, we have number 5 right here. So now we have a volume of a balloon, so we have the volume formula right here. Underneath that purple line is for the volume of a sphere. And then we have the radius increasing at a certain rate as well. So when we have this volume increasing, well, we can see that R is inside of volume, and our R is changing in its own way based on time. So we have to figure out, well, how time is changing, affecting the radius, and then take that answer, put it into R right there. So we want to do t seconds first. So let's do that. So now we have volume is in terms of radius, which is in terms of time. So we have that as our setup right there. And then we are going to do 4/3 pi. And then instead of a radius, we put in the function we are using for radius, which is 1/2 t cubed. And then we're going to cube that. So now this is a little bit harder to simplify. So we're going to cube the t cubed, and we're going to cube 1/2. So we have 4/3 pi is unchanged, and then we have 1/2 cubed. 1/2 times itself 3 times would be 1/8. And then t cubed times itself 3 times would end up being t to the 9th power. And so if we multiply across with our fractions, we have 4 over 24 pi t to the ninth. Well, 4 over 24 is just 1/6. So we have 1/6 times pi times t to the ninth. So a little complicated there. Hopefully you follow that. So now we're just going to put 3 seconds and 5 seconds into t for seconds up here. So if we are doing v of r of 3 seconds, it would be 1/6 times pi times 3 to the ninth. And so we can grab our calculator. So we have 1 over 6 times pi times 3 to the ninth power. So we have a balloon as far as volume goes that is very large. So we have 10,305.99, and that is we don't know if we units, so we'll just say cube units. We'll go with that. It doesn't seem like we have a length or a unit for our radius, but that's okay. So then we would just do the same thing and do v of r of 5. Going to be another big number here, so we have 1/6 pi times 5 to the ninth. And we would go back to our calculator and just replace our 3 with a 5. And you can see that we have a very large number for that next number there. Ends up being about 1.02 million, a little bit over that. So very large, but that is essentially how word problems work in this topic. Moving right along, we have, in some cases, you'll be looking at function composition using tables instead of just functions. And so we have an example here of a table where we have inputs and we have outputs for f, and then we have outputs for g based on those same inputs. So we'll go. We'll just skip the last thing. We'll just do the first with the ones on the left here. So we're going to do f of g of 1, g of f of 2, g of 1. So part A, f of g of 1 is basically doing f of g of 1. So g of 1, we'll just look for the x input of 1, and then go to g. Well, that would be a 0. So g of 1 equals 0. So then we're going to do f of 0. And then if we go to 0, the f output for 0 would be 5. And we'd be able to get that answer there. So just know that we knew that g of 1 would equal 0. And then f of 0 equaled 5. Moving on to problem C, we are doing g of f of 2. So we have to do f of 2 first. Well, f of 2 would be a 1. We're going to the f row. So that equals 1. And then we're doing g of 1, that answer. So g of 1 equals 0. So that means that this whole thing ends up being equal to 0. And lastly, problem E, we will do as well. And so problem E is going to be g of 1. So we got to do g of 1 first. So let's go to x equals 1. G is 0. And then we're going to do g of that answer, which was 0. So 0 going down to g ends up being equal to 1. So this whole thing equals 1. And the other problems would work very similarly to those. So that's how you would do composition of functions using a table. Next, we have graphs. So there's a lot going on in this graph. So we'll do two of those problems. So we'll do the two on the left here. So for part A, we are doing g of f of 1. So first we got to do f of 1. So f of 1, if we know that the this V-shaped graph, this absolute value 1 is f. You can see that the label is down right there. So f of 1, we're going to find 1. So f of 1 down here equals -1. And so from there, we got to take that -1 and evaluate for function g. So function g is this curvy polynomial looking guy up there. So -1 for g would be a 3, where my finger's pointing right there. So that means this would be equal to 3. And that means this whole thing is equal to 3. All right, question C, we are doing f of g of 0. So we got to do g of 0 first. So in our curvy problem, 0 is up at 5 right here. You can see that g of x at 0 would equal 5. And then we're going to take 5 and put it into function f. So for function f, 5 would go with a 1 as an output. So that would be equal to 1. And that completes that problem. And the whole thing would end up being equal to 1. And that's how you would do function composition with a graph of two different functions. And the last part that we'll cover in our video today will be kind of a reverse direction sort of problem. So h of x in all 6 of these are ones where you have a function within another function and you're trying to figure out, well, what are f and g that made it happen? So looking at number 47 for starters, 47 is saying that h of x is 2x plus 3 to the 4th. And we want to know, well, this f of g of h part means that we have f and then g inside of that. So the inside part of this one looks like it's this 2x plus 3 part, like that. So that means that our g of x would be equal to 2x plus 3. And then we have our f part. We would be putting 2x plus 3 into something. So we would just need to have an x to the 4th here. So 2x plus 3 would go into x, and then it would end up looking like h. And we'll do one more problem for this and to wrap things up. So number 49 is the one will be our last for this video. And we have h of x being equal to the square root of x squared plus 1. So that x squared plus 1 part is kind of the inside part. So that's what we'll call g of x, is that inside x squared plus 1 part. And then lastly, our f outside part will just be the square root of x. So you can see how it would have been taking x squared plus 1 and putting it into the square root of x and making it look like the h that we started with. And that concludes our last example. In this video, we have covered application word problems of function composition. We have covered function composition with tables and then graphs. And now we are doing the reverse, where we have the function composition being split apart into its two original components. Thank you for watching this video.